some of these. You don't have to, but if you wanted to, I'm going to put that on Canvas for you as well. So the first property I have is the addition property of equality. Okay, these first couple here, the first four, are all properties of equality. They're more having to do with algebraic proofs. Okay, so the addition property of equality is adding the same number to both sides of the equation. Okay, so if I have 5x minus 4, I'm going to leave a space here, equals 6x minus 2. When I try and solve an equation, I want to add this 4 to both sides so I can combine like terms. Okay, that's how you would go about solving that equation. Now when I'm adding that 4 to both sides, it's keeping that equation equal, and that's considered the addition property of equality. Okay, so adding something to both sides of your equation. Subtraction property of equality is subtracting the same number from both sides of your equation. So if I have 7x plus 6, again I'm going to leave a space there, and that was equal to 4. Okay, I'm just making these up. To get 7x alone, I would subtract 6 from both sides. Okay, so that process of subtracting 6 from both sides is the subtraction property of equality. The next one is the division property of equality. So that's dividing the same number on both sides. So say I have 5x equals 15. Okay, if I was trying to get x by itself or solve this equation, I would divide both sides by 5. Okay, when I do that, that's considered that division property of equality. The last property of equality is multiplication. So that's multiplying the same number to both sides of your equation. So if I had 1/2 x equals 4. Okay, to get x by itself, I would multiply by that reciprocal of 2 over 1 on both sides. Okay, right there and right there. So that process is the multiplication property of equality. Okay, any questions on these properties of equality before I go into the next ones? Yeah, up here. Next I have this substitution property. So you've seen substitution a couple times here. So if I have x is equal to y, then x can be substituted in for y in any equation, and y can be substituted for x in any equation. Okay, so that's like saying if I have x is equal to, say, 7. Okay, and I know I have, I don't know, this equation, 3x minus 2. Okay, then what I could do by the substitution property is replace your x in this equation here with 7. Okay, so then I would have 3 times 7 minus 2. Okay, so substitution is just replacing something with what it was equal to. Okay, so substitution is replace. The next one is the reflexive property. Okay, so for every real number x, x will equal x. So a number is equal to itself. Okay, that's your reflexive property. So I could say a is equal to a. Or I could say 4 is equal to 4. Now, the most common way that we use this reflexive property is when we're proving triangles congruent. So kind of like what we did on Friday. We're using side, 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 side angle, side, stuff like that, where we were looking to see if they had a side in common, right? In a proof, you would have to state that side is equal to itself. Now, you could do that by the reflexive property. Okay, so most of the time, this is how you would see it. A side is equal to itself, or a segment is equal to itself. Any questions on those ones? Okay, letter G at the top there is a symmetric property. So for all real numbers x and y, if x is equal to y, then y is equal to x. Okay, so it's just kind of flipping it back and forth. So if I had a was equal to b, and in my proof it told me I had to prove b was equal to a, I'd have to actually flip that around to say b is equal to a, and I would flip it around using that symmetric property. Okay, so it has to look like what you were trying to prove. Letter H is the transitive property. So if a is equal to b and b is equal to c, then a is equal to c. Okay, so if I had b was equal to 4. Okay, and I knew c was equal to b. Okay, so both of these right here are equal to b. Then I can say c is also equal to 4. Okay, so since both of those equal b, they must equal each other. The next one is the midpoint theorem. Okay, so if M is the midpoint of segment AB, then segment AM is congruent to MB. So here if I have a segment, that was segment AB, and M is the midpoint, meaning it's in the middle. Okay? M would then split that segment into two congruent pieces. So I could label each of those pieces with that dash mark showing that they are congruent. So here that conclusion that they came to was that AM is congruent to MB. So if you ever have that, you'd say that's by the midpoint theorem. The next one is definition of bisect. Okay, so this divides something into two congruent parts. We usually use it with angles. So if I have an angle drawn in here, and I draw an array that bisects that angle, that splits it into two different angles there. So I have angle 1 and angle 2. Now since that ray bisected that larger angle, these two angles I could say were congruent to each other. Okay, so angle 1 would be congruent to angle 2. Okay, so if you have definition of bisect, splits it into two congruent pieces. The next one is supplement theorem. So if two angles form a linear pair, then they are supplementary angles. Your keyword here is linear pair. Okay, there is a supplement theorem and there is a definition of supplementary angles. They are different. Okay, supplement theorem has to do with a linear pair. Now a linear pair forms a line. Okay, a linear pair forms a line and is made up of two angles. Okay, so if I had angles 1 and 2, since those two angles form a line, I could add them together and they would be 180 degrees. Okay? So since those are a linear pair, I can take the measure of angle 1 plus the measure of angle 2, and I could set that equal to 180. So those two angles form that line, so they add to be 180. The next one is definition of congruent segments. So if I'm given segment AB is congruent to segment CD, then I could say AB equals CD. Now the difference between these, this second one here has to do with its measure or length. Okay, so the other one's stating congruent segments. AB equals CD is talking about its measure. Okay, so what length it is. So this definition of congruent segments switches back and forth. So if I have my segment here, AAB, and my second segment, CD, and I know those are congruent. Okay, then if I was given AB is equal to 4, since those two are congruent, I could say then CD is also equal to 4. Okay, so since those are congruent, their measures are going to be equal, and vice versa. So if their measures are equal, I could say those two segments are then congruent. Yes? Okay, next one is definition of congruent angles. So this is similar to definition of congruent segments. It just has to do with angles. So if I have angle A congruent to angle B, then the measure of angle A equals the measure of angle B. So again, this switches from congruent angles to equal measures. So my picture, here's my first angle A. Here's my second angle B. Now if I knew those two angles were congruent, I'm going to label them with that dash in the angle. Now if I knew the measure of angle A was, say, 20 degrees. Since I know those two angles are congruent to each other, then I could say the measure of angle B is also 20 degrees. Okay, so if they're congruent, their measures are equal. The next one is definition of perpendicular lines. So this has to do with your lines that are perpendicular. Okay, there's a couple different ones in here that you may get mixed up with definition of perpendicular lines. Okay, that has to do with the lines. So this is two lines that meet at a right angle. So if I have two lines, they meet at that right angle, they are perpendicular. That's the definition of perpendicular lines. Okay, the next one is definition of a right angle. Okay, this is different than perpendicular lines. This is just saying an angle that is equal to 90 degrees. Okay, so if you had, if you were given that angle A is a right angle, okay, you know it's a right angle, then you could say, well, then the measure of angle A equals 90, because that's the definition of a right angle. Okay, definition of complementary angles. These are two angles that add to be 90. Okay, so for this one, I'm going to draw in a 90-degree angle and put this box in the corner. Now for complementary angles, I know I have to have two that add to 90. So I'm going to draw an array, splitting that angle into two different ones. Okay, now that doesn't mean that it's bisecting that where each of those is 45. Okay, it's just array, splitting that angle into two different ones. So if I label this angle right here as 1 and this one as 2, I could take the measure of angle 1 plus the measure of angle 2, and it will equal 90. Okay, so I can add those two angles together to be 90 degrees. That's the definition of complementary angles. The next one is definition of supplementary angles. Again, this one is different than supplement theorem. Okay, so I'm going to draw it a little bit differently. So definition of supplementary angles is two angles that add to 180. Okay? In your supplement theorem, yes, those two angles do add to 180, but they have to form a linear pair. For definition of supplementary angles, they don't need to form a linear pair. So I'm going to draw these angles separate. Okay, so I'm going to label this first angle as 80 degrees, and I'm going to call it angle A. My second angle, right here, I'm going to label as 100 degrees and call it angle B. Now, if I add those two angles together, so the measure of angle A plus the measure of angle B, 100 plus 80 would be 180, and those would be considered supplementary angles. Okay, so unlike supplement theorem, these two don't need to be next to each other. Okay, supplement theorem has to form a line. These two don't. The next one is segment addition postulate. Okay, I'm not going to read you that whole thing. I'm just going to show you what it is, and I think it'll make more sense. So if I have this segment here, and I call it a C, and I have a point that is between those two endpoints. Okay, not in the center, but just a point between those two endpoints. What I could do is take this segment AB, so that length right there, just AB. I can add on B to C. Okay, so if I add those two smaller segments together, it will equal the entire segment of AC. Okay, so I can add together those two smaller ones to get the larger. That's what that segment addition postulate is saying. What do you mean? Yeah, you're home. Yeah. It won't be super difficult. All right, next one is angle addition postulate. So it's similar to that segment addition postulate, but we're working with angles. So I'm going to draw in an angle here. You okay?
Someone's dying.
Okay, I'm going to put a point here, A, a point here, B, and a point here, C. Okay, this is going to make it a little bit easier when I try and tell you what's going on.
Yeah.
Now I'm going to draw an array, splitting that angle into two. And I'm going to put point D on that ray. Now, according to this angle addition postulate, what I can do is take this angle A, B, D. Okay, so that first angle there. So we're going to take the measure of angle A, B, D. We can add on this second angle right here. So angle DBC. Okay, so those two smaller ones that I created, we can add those together, and that should equal the larger angle that I drew in first. Okay, so the measure of angle ABC. Okay, so two smaller angles that make up that larger, I can add them together to get that larger angle. The next one for the right angle theorem, the part of this one that you're mostly going to use is that all right angles are congruent to each other. Okay, so all right angles are congruent to each other. So if I have a right angle here, A, and another right angle, B. Okay, so if I'm given angle A and angle B are right angles. Then I can say angle A is congruent to angle B because all right angles are congruent to each other. So if A is right and B is right, they are congruent because all right angles are congruent. Does that make sense? Okay, that's the part that you guys are going to use most often. The next one is the vertical angle theorem. So vertical angles are always congruent. So if you have a picture, okay, where you have two intersecting lines.
Let me guess, angle A and B.
No, I'm just going to mark them. So I have this first angle here, the second angle here. We can do 1 and 2. Since those are across from each other and they're created by two intersecting lines, they are vertical. So I can say angle 1 is congruent to angle 2 by the vertical angle theorem. Okay, most of the time when you're using vertical angle theorem, it's one of your freebies. So like the assignment from Friday, you had those two triangles and you had angles 1 and 2 were vertical. Okay, you could say they're vertical by the vertical angle theorem. Okay, it's usually one of your freebies in your picture. Okay, the last ones have to do with parallel lines. Okay, so you guys did parallel lines last year. Okay, so our properties for these are if lines are parallel, then your alternate interior angles are congruent. If they're parallel, corresponding angles are congruent. Alternate exterior angles are congruent, and consecutive interior angles are supplementary. So if I have, and I'm given these two lines are parallel, okay, so those two lines are parallel, I'm going to draw in these arrows to show they're parallel. Okay, so those arrows in your line shows that those two are parallel. And if I have a transversal drawn through those two parallel lines. Okay, I'm going to label some angles here. So if I have angle 1, we'll label this one 2, this one 3, 4.
Right.
I think that's all I do.
Alright.
What? No? So, given these, okay, so if I know I have parallel lines, I could say for my alternate interior angles, that's why I missed one. Should be 5.
Yeah.
Sorry. I could say angle 2 and angle 5 are congruent. Okay, so angle 2 is congruent to angle 5. Okay, those are your alternate interior angles. Now if those lines are parallel, I could say my corresponding angles, so 2 and 4 are congruent. My alternate exterior angles would be 1 and 4. So angle 1 is congruent to angle 4. And then my consecutive interior angles, so 2 and 3. I could say angle 2 is supplementary to angle 3. Okay, so with your consecutive interior angles, those two add to 180, they're not congruent. Okay, those are your only ones that aren't congruent to each other. For the last one, it's just the opposite. Okay, so if you're given that those angles are congruent, then you could say those lines are parallel. Okay, so if I have these two lines with a transversal, again, I'm going to label my angles 1, 2, 3, 4, and 5. Just the same as I did last time. So if I knew that angle 2 was congruent to angle 5, then I could say those lines were parallel. So it's just the opposite of that other one we did on top there. Okay, that one we were given parallel lines. This one, you're given the angles and you're proving parallel lines. Okay, so those were your alternate interior. Your corresponding angles are 2 and 4. So if angle 2 is congruent to angle 4, then your lines are parallel. Your alternate exteriors, so if angle 1 is congruent to angle 4, then those lines are parallel. Okay, last one is consecutive interiors, that's 2 and 3. So if I have angle 2 plus angle 3 equals 180, then those lines are parallel. All right. Is this kind of stuff coming on kind of back to you a little bit?
I guess. Well, I'm gonna say this. I don't want to get
All right. So what I have for you, they're called one-step proofs. They're just using these properties that we went over. Okay, so I'm going to help you with the first couple just to get you started so you know what you're doing.
I'm not talking about this. I'm talking about my English test.
That's a good strategy as well.
Well, it's not English, it's like writing. My weekend was horrible.
All right, so if you look at your sheet, wow, it's a great color. So what you're doing is reading what you're given and then the conclusion they came to. So in the first one, I'm given if M is the midpoint of segment AB, and they're concluding that AM is congruent to MB, you want to state the property or reason how they came to that conclusion, and it is the midpoint theorem. Okay? So with these one-step proofs, you do want to just kind of pick out those key words. So if they say like vertical angles or something like that, you want to pick out those key words so that you can better find that property in that packet. Okay, does that make sense? So all of the properties on here that you're going to use were in this packet. Okay, not all of them are going to be used, and yes, you're going to use some more than once. Okay?
I can't find the next one. Can you do the next one too?
You can't find the next one?
Do like
So-
the first three.
Not doing the first three. So if angle ABN is congruent to angle NBC, their conclusion was ray BN bisects angle ABC. So if you have a ray bisecting an angle, splits it into two congruent parts, which one splits into two congruent parts? Definition of bisect would be number 2.
Yeah.